Good morning. In this session, I would like to demonstrate a heater model and a heat exchanger model available in Aspen. I may be taking the same example even to demonstrate the heater model. So a process fluid containing methanol and water with this composition need to be heated from 25 degrees centigrade to 70 degrees centigrade at the rate of 1000 moles per hour. Design a shell and tube heat exchanger. So let us see how to go about this using Aspen. The two components that we are trying to use are methanol and water. So having defined both the components, you can go to the next input screen and specify the property model. Go to the next input screen, go to simulation environment. And first of all, let me take up the case of a heater. It looks like, as you can see, the heater model will not be able to do the design calculations, but it will be performing the required mass and energy balances. Again, it will not address what type of heat exchanger you are using, what type of area, how the utilities are required, what kind of utilities are being provided. So some of these issues are not part of this particular heater model. As we have seen with respect to some of the simplified models earlier, like component separator, stoichiometric reactor, this is also something similar to that. Normally, we will be using such simplified models for performing preliminary mass and energy balances. Once the mass and energy balances came to a convergent solution, probably at a later stage, you can replace this unit with a unit or model which is capable of doing the design calculations. So don't try to make your simulation complex right in the beginning. That's the normal process that we'll be using. So let us go into the specification of the problem for this. Now we are required to specify the streams, one stream, input stream, and also some information with respect to the block. So we have 25 degrees centigrade, maybe pressure is not mentioned, so we'll assume atmospheric pressure, 1000 moles per hour. 25 degrees centigrade, let us say 1 bar, 1000 moles per hour. And we know the composition. So let me take it as weight percent, 0.368 and 0.632. So we have defined the stream. So let us go to the next input. Now we are talking about the block. Now these are some of the variables that you must be in a position to define. You can define any one of these: temperature change, duty, vapor fraction, degrees of superheating, degrees of subcooling. Right? Similarly, any combination of these you should be in a position to handle. So the outlet temperature is 70 degrees centigrade. So let me specify this. And the pressure is, what do you mean by mentioning zero pressure? This kind of a notation is common across Aspen. Whenever you put zero, it will be taking it as a pressure drop. Any value with a negative sign specified for the pressure is taken as that much pressure drop. Any positive value that you type will be taken as the actual pressure. So writing this as 0 or 1 has the same meaning, because the input is at 1 bar. When you say 0 pressure drop, the output would be at 1 bar. And it is same as when you say 1 bar, because the output now will be at 1 bar. So if you want any vaporization, condensation, you can specify. Otherwise, you can also specify liquid only. In this problem, I think it is going to be liquid. So let me go ahead and run the simulation. So we got to our results. Now you can see the stream summary. So the inlet stream, which is coming at 25, is being heated to 70. Now you can see the molar vapor fraction is 0, liquid fraction is 1, and the pressure, there is no pressure drop. Obviously, there will not be any change in mole flows or mass flows because there is no chemical reaction happening. But what about the other details? Let us look at the results of this block. Now you can see this is the amount of heat duty. What do you mean by positive value? That much of heat must be supplied to the system according to your thermodynamic notation. Now as long as, irrespective of whether you are using a simplified model or maybe a complex model, the energy or the heat duty will not be changing unless probably you revise your property model. So this kind of calculations can be done quite quickly, perform mass and energy balances using this kind of a simplified model. So let me deal with another small heat exchanger model by deleting this block and replacing it with the heat exchanger model available in Aspen. So let me connect the streams. Before that, 1 second. You can see. So this is the inlet to the cold fluid, this is the outlet of the cold fluid, this is the inlet of the hot fluid and outlet of the hot fluid, right? Already we have defined the stream, so I am trying to reconnect. Now I'll be adding, remember the heater model was not, sorry, let me also show you the block results. Earlier, I missed this point. It is not available. Actually, when you try to see, the energy balance performed with heater model will not be, the energy entering is not equal to energy leaving because we are not addressing how the required heat is added because we did not add the utility part of the fluid. But that is not the case in this heat exchanger model. Once again, if you try to see, there are two input streams, 1 and 3, and we need to specify both of them. Remember, I have already specified stream 1 based in the previous problem, 25 degrees centigrade, 1 bar, 1000 moles per hour with this composition. But we need to specify the stream 3. That's why this is turned into red, and there is a change in the block, so we may have to provide some information even with respect to this block. So let us go ahead. Next. Because I did not specify any other component, let me take water, the maximum water or steam, the maximum temperature, you can say probably vapor fraction 1, saturated vapor maybe at 2 bar. This is a wild guess. The flow rate is because that was 1000 moles per hour. Let me also take 1000 moles per hour of steam. I hope the necessary heat duty will be able to meet from this stream. Otherwise, we can revise. So this is fraction or mass fraction, pure water. So the utility fluid has been assumed to be saturated steam at a pressure of 2 bar with this flow rate, right? Pure component. Now that should take care of stream 3. Go to the next. Now, there are several options you can verify. In fact, you will be able to access the exchanger design and rating by selecting the shell and tube. We will be able to do only shortcut design without going into the shell and tube exchanger design and rating part. And you can also do some calculations with this. So I have selected, for example, if you want to go into detail, so this option is not available if you want to perform detailed design calculations within this model, right? Similarly, when you press air-cooled plate, some of these design options are not available within this model. Automatically, exchanger design and rating will be activated. So that can be done. So if you want to use this model, at least one of these specifications is mandatory. You can specify any one of them. So we have cold stream outlet temperature. It is entering at 25. We wanted to heat it to 70. At least any one of these variables, depending on your problem statement, you can specify. So would you like to handle it as counter current, co-current? You can specify this. Where do you want to put your hot fluid? Maybe on the tube side. If it is condensing, you need to put it on the shell side. You can take care of some of those common decisions while designing this problem. Let us go ahead with this. Now you can see all the required input is complete. You should be able to run the simulation. Don't worry, that was because of the previous one. Now let me go into the details. So what is happening? Stream 1 is getting heated from 25 to 70. Stream 3, practically there is not much of it. That means we are using too much of flow rate at this high temperature. So from this, you can also specify what is the other results. Now you can see exchanger details. So the required exchanger is quite small, especially when you are using high temperature steam. Probably if you use maybe hot water, things may be better. Anyway, just to demonstrate only, I am using this. And what about this overall heat transfer coefficient and the LMTD? Correction factor by default is taken as 1, so it will not be able to calculate the actual correction factor. And what about this heat transfer coefficient? So this is the area. So whatever it tries to do this. If you go into the exchanger, in fact you can see we did not mention, you can also specify what if you have some pressure drops on the hot side and cold sides separately. In case if you want to take into account the pressure drops in the real case, that is also possible. But if you try to look at these U methods, by default, irrespective of the system that you are handling, a constant value by default is taken by this model to calculate the area. Or if you want to go ahead, only when you specify the proper value of overall heat transfer coefficient, you will be in a position to calculate the area of the exchanger. Remember, the design details are limited to only calculating the area, but you will not be able to do other calculations like shell diameter, tube diameter, number of tubes, and so on. Now you can see the mass balance and enthalpy balance are 0, but in the case of heater, you can observe this energy balance will not be satisfied because we are not addressing how the required energy is added to the system. You can probably explore, these are very simple models, but you can identify the limitations of the design that you will be able to perform using the heat exchanger model available in Aspen. Now the moment you click here, there is a possibility you select shell and tube. So what type? Then size exchanger, select conversion method, size interactively. Now if you put some name here, automatically you will be able to open exchanger design and rating, which you have seen in the detailed design of the heat exchanger. Either you can handle the design from here or design the heat exchanger separately using that module. So with this, I would like to stop this session.